Hello, everyone. Thank you for having me. I'm happy to be here talking about my work with Jack Carrett and William Farmer on creating generative tools for library building. So I'd start by claiming that large libraries of mathematics are useful but are hard to build. And I'm sure most of people here will agree with that. And because they're useful, we have many visions for building libraries of mathematics. In 1994, the very influential QED manifesto was released, and with the vision of formalizing all of mathematics in one library. And I mean, the word all of mathematics is definitely not like with all the applications that we're talking about these days is a big word. And also having one formalization for them is a bit problematic. So there is the refined version of that, which is building a universal digital mathematical library where libraries like different pieces of mathematics are formalized in different libraries with different foundations, but those libraries are able to communicate with each other and results can move from one formalization to another. But we're still not there yet because libraries are hard to build, and beside the technical problems of choosing foundations and choosing organization structure, there is the problem that there is a huge amount of knowledge in mathematics. In building a library that contains most, if not all of that, is definitely labor intensive. But is the effort being put in building those libraries actually optimized? I would claim that no, because libraries of mathematics, we have many libraries of mathematics, but there is a lot of redundancy within a library and between the different libraries. And I want to elaborate more on that. So this is the definition of monoid. It's one mathematical concept, and here are the definitions in 5 different languages. And we can see that even within the same language, there might be more than one definition of monoid. And within the different languages, the definitions looks very different. And but why do they look very different? It's not because monoid is different in each of these languages. It's more because there are the design decisions that are baked in those definitions, and that makes them look different and make the way they are used different. So for example, the bundling problem is like a famous problem of like where to put the declarations, whether they should be part of parameters to the structure, or like here, this axiom being like part of that structure, being a field of the structure. So every system, they take their own like approach. The most popular one is having the carrier over as a parameter, but that's not like standard. In many cases, like over here in one of the calc libraries, it's not. And there is no agreement on which one is better. Another one is equality. Do we want to have a fixed equality for all the structure, or we want to do like EGDA here, where we work on setoids and equality is passed for every structure, and so it can be different. Another one is the algebraic structure. So look here, the monoid is defined as an extension of semigroup, and the same in Haskell, and I believe somewhere else in MMT over here. But again, it's not standard. Not all libraries do that, and not all users are actually interested in dealing with monoids as extensions of semigroup. Maybe a mathematician who's only interested in monoid doesn't want to care about the semigroup structure. And even within that same monoid structure, having only monoid in our libraries is not very useful. We usually have some of the tools that are associated with it, or some of the constructions associated with it, like homomorphism. That's the definition of monoid homomorphism in MATLAB, and that's the definition of additive monoid homomorphisms in the same library. They look very similar, but a human being had to just like put this and that and provide it for all the other theories that we're interested in. And another useful structure is the product. And although like MATLAB has at least 15 definitions of products, I wasn't able to find the product for additive monoid. So that's a problem, that those structures are like costly to provide, and in most cases there is no like uniform way of like having them for all the theories that they were interested in. So can we do differently? Can we actually have those definitions generated for us. That's what we want to have. We have a vision of building libraries that instead of the library developers actually providing all the definitions of the library, they will provide a description of what they need in the library. Something like, I want to create Monoid as an extension of semigroup, and I want to have only the carrier as the parameter. And then those definitions can be generated. So to do that, we really need to understand the design decisions that library builders take and how those design decisions affect the building of the library. And in this, we're kind of inspired with what Haskell does with deriving tools for data types. Like if you define a list data type, you can get a set of tools, including equality, imprinting, and others, and also setters and getters for data types. You kind of specify with putting an underscore that you want a setter and getter for this field, and then the lenses library would generate that to you. And to do that, they use meta programming template Haskell in this case. So this, to satisfy this vision, we really need to understand, is there one abstraction of Monoid? Is there a way to capture the essence of Monoid, abstracting over all those design decisions, and then and operate on it and be able to then put those design decisions back as needed? And if we aren't able to do that, what information do we need the library builders to provide, and which information can be generated? And is there enough information to be generated? Is it even worth it? Will it actually change the activity of library building? And luckily, we have a lot of those answers in universal algebra. So we know from universal algebra that a theory, or at least a unisorted first order logic theory, can be described as a tuple having a sort, a function symbol, a list of function symbols, and a list of equations. And then homomorphism, we have a uniform definition of what a homomorphism is, as a function from one sort to the other, the sort of one of the algebras to the other. And then for every operation, we need to generate that preservation axiom. So theoretically, we do have a way to generate a homomorphism from a theory presentations. And we need to put that, or to automate that in the process of library building. So our interpreter, or the interpreter that we're suggesting here, has three phases. First is the flattener. So we take a description of a theory, like we want to create Monoid as an extension of a semigroup. But this definition will not set it, if we only have this definition, we cannot apply universal algebra abstractions on it. So we need to flatten it. So the first phase is flattening this description. And then we end up having a theory graph where the theories are flattened, but there are still morphisms that keep their relationship to each other. And then we can operate on those flattened theories with the generator and generate all the useful tools that we already know how to generate from universal algebra. And because we are working on abstraction, we don't want to be burdened with design decisions because we want to be able to use this abstraction in different setups. The third phase is an exporter that will put back the design decisions that we abstracted on, so it becomes more useful to users and actually export it to the languages that they desire. And to build that interpreter, we needed a language, a small language that enable us to kind of overlook design decisions or abstract on them. And we need a large library of theories so that we can formalize it or have our interpreter work on it, and meta programs to manipulate the theories in this library, and definitely a TypeChecker to check that what we're generating makes sense. And for that, we choose Tog. We actually had a hard time choosing the abstract language because we wanted a really small and toy language which we can operate on and write meta programs on. At this time, we didn't really know about Lean, or didn't do enough experiments on it. It seems like Lean is a very good alternative, but for now, our work is implemented in Tog. And Tog is an experimental language in the style of Agda, so it's based on Martin-Löf type theory. It's dependently typed, And here I give an example of the formalization of monoid in Tog. I mean, you can see it's pretty readable and pretty minimal, and you don't have a lot of details here. So talking about the different phases of the interpreter, the first phase is a flattener. And again, working with our like running example, the monoid, this is what a theory graph for building monoid looks like with a tiny theories approach, where we always add one piece of information at a time. And that's, I mean, doing that would actually optimize the connections, would give us more connections between theories. And so when we define monoid in our setup, we don't only get the theory of monoid, we actually get all those theories and arrows in the graph. And let me show you how we do that. So we first have our carrier theory and we have our basic extensions. So we extend carrier in different ways. And we define semigroup as an extension of Magma, which is the thing that most formal systems would allow you to do. And then we want to create pointed Magma as an extension of both pointed and Magma. And to do that, we use an operation that we call combine that is basically a push out. So we combine the definitions of pointed and the definitions of Magma with the common part being carrier. So carrier is only included once. And we repeat those like with extensions and combines, we can actually just build that graph that we were talking about for a monoid. But things get a little tricky when we have renames. So what if we are combining additive Magma and semigroup over Magma? What would be the result of that push out of that small square? We know that we're combining over Magma, so we need to have one carrier and we need to have one binary operation. But should we call it up or plus? What should we do in this case? We actually can resolve the name conflicts in different ways, but in this case, we want to have additive semigroup. So we want to signal through the push out to rename that up to plus and rename it within associativity to also plus and use those in the push out. And in this case, there is no name conflict and we just have the normal additive semigroup that we would expect. After we have, so we do that on all the theories that we have in our library. We have 227 theories, and then we have those theories represented independently as dependently typed records in Coq. We want to operate on them using universal algebra rules, so we need them to look like equational theories in the same definition that we just gave. So we have that data type with the name of the theory and the three components. It's stored the list of function types, and the type constructor has a name and expression, which is the type of the field that has the name. And we have the axioms. Again, it's a list of constructs, and that waste would signal out how many, would let us know how many parameters are there for that theory. And we need that piece of information to be able to access them later, whether we need to project them or not. And this is how we generate homomorphisms from that data type. So the input here is an equational theory. And then our frame, excuse me?
The waste thing?
Can you say that again, sorry?
You went a bit fast with the last parameter. Could you
sure.
The waste thing?
Yeah. So the waste is a number. It's an integer that just tells us how many of these so we have a sort of function type in axioms. We know it's a telescope, so they go in order. But how many of these are parameters? For example, in the case if only the sort is the parameter, the waste will be 1. If it's 2, then the sort and the first function symbol. And we need this piece of information because later when we do homomorphism, for example, we need to access those fields. We need to generate preservation axioms for them. And accessing those fields will to access those fields, if they are fields, we need to qualify them with the name of the instance. If they're parameters, we don't need to. We just access them because they'd be hidden binds or hidden inputs, hidden parameters. Sorry, that's the word. I know in Lean we don't really need to qualify, but because we're working in a more abstract setup, in other backends like in Agda, we need to qualify. So that's the thing that I needed to align in the exporter. Okay, so yeah. Does that answer your question?
Yeah, thanks.
Okay, thank you. And this is, yeah, so one of the things we generate is homomorphism, and this is the function that we use to generate that. So the first thing we need are the instances, and our framework provides that back, like that tool of creating, or like that function that creates instances for any equational theory. And you're like, that number would qualify it. You can qualify it or not. So like you can have like something like monoid M1 if you send the A1 and monoid M2 in this case, or just send nothing and have M. And for every instance, we have its name, its binds, and the expression that refers to the instance. So like its name and the parameters that are part of the binds. And we do that twice for the two instances. And we use them as, so like here we create a tog record, and we just use those binds as like the hidden parameters over here. And we get the names and the expression to be like the explicit parameters to the homomorphism. Sorry. Then the next thing we do is generate the homomorphism functions. We definitely have our helper functions to do that. And then have our preservation axiom, that function that generated for every operation or every function type, or we just map it on all the list of all function types. So I mean, once we have that infrastructure in place, the definition, the ways we generate definitions is very intuitive and correspond to so much to how the universal algebra definitions work. So I see that I'm running out of time.
You started 10 minutes late, so don't worry.
10 minutes?
Yeah,
Okay.
you don't
That's
worry.
good, thank you. So next, so yeah, homomorphism is one of the things that we create. We do create other things. So like over here are the things that our framework actually create. We have term languages and some of like simplifiers and evaluator induction principles in products. And there are other things that can be generated, but are not implemented yet. And I have a list of them down there. The last phase of the interpreter is the exporter. And we have like, so we implemented a type class export for every type in the AST of TOG and we do now export to Lean and Agda, and the only difference is in the configuration file. So just by changing the configuration file, you can get another backend, and that's a lot of saving of writing. And to do that, like, so like the configuration file was not the only thing that was useful. We needed to have those functions that are implemented for both Agda and TOG, but are called once. One of them is like a replace function, because they have different names. For like nat in Agda is uppercase, in Lean is lowercase, but they can both use the math BB symbol. They call function, and this one checks for all the function calls. It's called before every function calls, mainly because of the exported function. So, sorry, imported function. So when we import a function, sometimes there is a difference in the order of arguments, like the lookup function. If you want to look up a value inside a vector, so in TOG, it's like the value first and then the vector. In Lean, it's the vector first. So those alignments need to be done for every different symbol. So call func is another function that needs to be provided for the different backends. And then we have the pre-processed declarations, and that line is also for aligning the big declaration, like the inductive types or the function definitions, which, sorry, in the case of Agda, you would have them like, you would have something like that inductive type, you would have an A at the end, but in TOG you don't. In Lean you don't. So those are what another differences. They needed the abstract syntax tree of TOG to be adjusted before printing. So before we do any printing, we call the pre-processed declarations function to do that alignment. But if we're adding a new system to export to, we don't need to like re-implement the exporter. We need to provide a configuration file and implementation of those three functions. Using this interpreter, we were able to start with 227 theory expressions. That's 227 lines of code. And we generated 5,092 library definitions with over 32,000 lines of code. And that's only in TOG. We were able to export that to Lean in Agda. And I want to I will try and show you now the output. So let me do that here. So that's the monoid definitions that we just saw on the slides. And those are like 10 lines of code. And when I try to export it, so I set the mode to interpret, and then the output language to be lean, and I give it a target folder, call it lean generated, in the file demo.talk. And we can see that it's like, so this is the last command. It has been generated. And if we go to lean generated and list the files here, we have like all the files that has been generated. These are 11 files, the 10 definitions here, and one preload file. And I'm interested in showing you the output, the lean output. So this is all generated code in lean. It's pretty readable. There are definitely like some problem with our choices of the name, but that can be better. But those are, so like we have the definition of monoid, its signature, its product, the homomorphism, relational interpretation, term languages like closed term languages and open term language with access to the carrier elements or not, and simplifier, evaluator, induction principle, and staging. And all that is just, again, generated in Agda. And with doing this, we don't only have it to monoid, so we have it to every theory in the graph. So we have it here again, the same information for semigroup. And so let me go back to the slides. So those results show how a generative approach is actually very useful when building libraries, and that we can get those boring tasks out of the way of library builders so they can actually work on the interesting part of formalizing new pieces of mathematics. And the way to do that is to actually abstract over design decisions, work in a small abstraction, and have a strong way to meta program structures to generate those constructions that we know can be generated uniformly from the theories. And for future work, we definitely want to generate for more definitions. There are more definitions even outside universal algebra that we can generate to. Another thing is that when we generate homomorphisms, we don't connect them to the theories in the graphs. The working on generating those morphisms is another useful thing that we can have. We can definitely export to more formal systems. And for that, we're envisioning like a study of formal system as program families where they are the same but different. There are a lot of commonalities between them that we can take benefit from, but we need to study it. We need to do some domain analysis when it comes to that, so we can optimize exporter and minimize the work that we do to generate, to like create more languages or create more libraries, sorry. And there is definitely the higher order logics like generating functors for categories. Those things are like, again, they are studied in the literature, but they're not implemented. So we envision generating monoids in theories, something like that, where we have we define how they are connected to other theories in the library. We define what we want to generate from them. We give some design decisions that we want to use, and we just specify what language we want to export to. And maybe that would make the process of library building much easier and better, and just save efforts. And those are some of the references for people who want to read more about that. And yeah, thank you. Questions, I believe.
Thank you very much. Are there any questions?
I've got questions. I have got two questions. So firstly, so thank you for your talk. It was nice. Last year we had a talk by Cyril Cohen about his joint work with Saguchi and Tassi, and about this, which has some intersection with what you're doing. And I'd like to know if you could comment on that. And the other question is, so it's true that in all the theories that you explained, that monoids and groups and stuff, that we have a lot of repetition, but but we get it right on the first time. Whereas as soon as we move to, say, modules where you have two types, then we have difficulties. I mean, we need experts to know, to make sure, for instance, that the type class mechanism is not going to start looking for a ring structure on a completely unknown type and then run wild and do stupid things. So is your work also going towards handling things like modules and more complicated things where you have several types?
Okay, I'm not aware of the work that you were talking about. So can you give me more details about what it does?
I think Cyril is around, so maybe he can tell us. Is he around? Cyril, are you here?
But if he's not, I could potentially answer.
Okay.
And in particular, I mean, one thing.
Cyril says he is here, but doesn't have mic and video.
Okay, yeah. I mean, it's also generating stuff through metaprogramming, but it feels more dynamic. In particular, you don't need to decide in advance everything you have, and you can sort of add intermediate stages after the fact, and the interface won't change too much. Stuff like that. But I don't know, maybe Jacques knows.
Are you talking about the hierarchy builder?
Yes, hierarchy builder with
Yes. Okay, so now I know what you're talking about. Sorry. So I know about that work. I believe, as far as I read, their main focus is on maintaining the hierarchy in the library. So they solve like one of the design decisions problems that we were talking about. Our approach is like it's different in the sense that we're not only focused on that problem. It's more of abstract away all design decisions. The second thing is we start like using the combinators to build the hierarchy. We do have a graph, so that's like an underlying data structure, and this graph should be working to transport results from one theory to another. But when we the theory that's facing the user is the flattened theories. They do have access to the graph if they want, but I mean, I just imagine like a mathematician who wants to work in group or ring and doesn't want to be burdened with all the details of defining things in terms of the hierarchy. They only are interested in just like the theory they're working in. So it's more of we don't give like solid maintainability solution for the problem of changing the hierarchies, but our solution is more of the hierarchy can change, but the theory facing the user will still be the same because it will still have its own, like, it's the same definitions. Ring will still be like ring with the same definitions that are there. And maybe Dr. Brett will have more to say about that.
Does Dr. Karat have anything to add?
Well, so I guess I should say that there was a DAX tool some time back where Cyril and I had a lot of conversations. So of course there's a lot of overlap because we're kind of starting from many similar ideas. And I gave a talk on something related to this beforehand. As far as the question about module homomorphism, that is indeed much more difficult because there are more moving pieces and there's some open theory still need to be done to really look at a telescope as being cut into pieces where some pieces are to be mapped and some pieces need to be fixed as having a constant mapping. And so there really is some sort of higher order universal algebra on telescopes in dependent type theory that currently some people are looking at, but not from this kind of computer science view. And so that's not in scope for Yasmine's PhD thesis, but is kind of in scope for the things that I'm looking at for the future. But as far as I know, this theory has simply not been done yet.
So it's probably time to wrap up. But firstly, thank you very much, Yasmine, for your talk. And I did have several other things to add, but I think it's probably best if we don't add them now.